We're now going to turn our attention to yet another example, and this will be an example that will demonstrate, once again, the n times q model to show why you need large N and ideally large Q in order to be able to get a win from parallelism. This particular example is interesting because what it's going to do is it's going to end up computing factorials using big integers. So we can compute some pretty gigantic big integers and factorials for big integers. And we're going to demonstrate a couple different ways to do it. We're also going to show what happens if you're not careful and you have unsynchronized data that's being accessed and updated by multiple threads at the same time. So let's go ahead and take a look at the program. We're going to have a number of different factorial implementations. We're going to have Buggy Factorial. We're going to have synchronized parallel factorial. We're going to have parallel stream factorial. And then we're going to have parallel stream factorial EX. And I think there's a couple other ones. We got one more, sequential stream factorial. So those are all the different types of factorial examples we're going to do. Let me go ahead and run this just so you can see the behavior, and then we'll look at the source code. So what we're doing here is we're computing the factorial for 400. We want 400 factorial. And you can see that we've got the results here. I probably should have sorted them, but in essence, it took us 1,613 milliseconds to do the synchronized parallel factorial that uses the synchronized statement. The sequential factorial took 613 milliseconds. Buggy factorial was very fast, but the result was wrong, as we'll see. And then it took us 347 milliseconds and 404 milliseconds for the two parallel streams factorials. So let me show you the other funny thing. So you'll notice that one of these results is not like the other. So the Buggy factorial, which ran pretty fast, produced the wrong result, whereas all the other ones gave us the right result. So that's what we're doing. We're computing factorials with different mechanisms. So let's go ahead and take a look at the different mechanisms that we're testing here. Let's start off with Buggy factorial. That's a good one. So we'll start off with the bug. I think that was at the beginning. So Buggy factorial is going to violate every possible rule of parallel streams, and it's going to have mutable shared state that's unsynchronized. That is the root of all evil in concurrent and parallel code. So how do we do this? We're going to have a class called Buggy Factorial. It's going to define a nested class called total, which is going to have a big integer called mtotal, and we're going to go ahead and update it by calling multiply on this. You'll notice there's no synchronization in its sight here. So here's our factorial method for the Buggy Factorial, and it's going to go ahead and generate values from 1 to n, where n is a long, so this would be very large numbers. It's going to run everything in parallel. It's going to turn each big integer, going to turn each of the longs into a big integer, and then it's going to go ahead and multiply these things in parallel using the call to this method. Because this method is not synchronized, chaos and insanity ensue, and the results are nonsensical. So it's fast, but completely wrong. There's also some problems here because this code is not properly synchronized either. So bad news, don't do it this way. So we might think, well, we can fix this by putting a synchronized statement or a synchronized method here. So this is the synchronized version. And you'll see all we do is we take the multiply method and we just wrap a synchronized keyword around it. So we now have the synchronized keyword for a synchronized statement. And this version is in fact correct. We do the same thing to get the result back with the get method. Here's what it looks like. It looks pretty much identical to what we did before, with the differences being that the multiply method is now synchronized and the get method is now also synchronized. This gives us the right result, but as you saw when we ran the tests, the performance is dreadful. And that's because we have a contention point where we're synchronizing on the same object every time we do this in all the different threads, which is obviously not going to scale. Now let's take a look at the parallel stream factorial. And I guess first let's look at the sequential stream factorial. This is just the classic sequential stream way of doing things. You create a range of values from 1 to n. You map each of these long values to a big integer using the value of helper method, and then, or factory method. And then we go ahead and use reduce. And reduce is this cool terminal operation that will start with the initial value, which in this case is 1, and then we're going to pass in the multiply value. So we have the multiply value of big integer, except this is now done carefully in a way where we never have to worry about shared mutable state. And that's because reduce creates immutable objects that are inherently thread safe. So there's never any contention, never any shared mutable state, never any race conditions. So that's the sequential version. And we saw that the sequential version works, but it's not as fast as we might want to be. Now let's go ahead and look at the parallel versions. They're the ones that are really interesting. So here's the parallel stream factorial. You can see it's absolutely identical to the sequential version with one little minor change. We say make this parallel as opposed to make this sequential or keep it sequential. But otherwise, it's identical, and it just performs so much better. And that's the wonderful n times q phenomenon. And then down here, we use another variant. This is the 3-parameter variant of reduce. And once again, there's no shared state. And I think if we see the performance, they're roughly about the same. So not really a big win going either way. So those were just some interesting examples illustrating the uses of these mechanisms. Just for kicks, let's come down here and let's see if we can change the number of elements that we're going to be doing. Try to see if I set that programmatically anywhere. Let's see. Here we go. So I can set this. So just for kicks, let's go ahead and pass in, like, I don't know, 10. We're going to compute 10 factorial. And so what you can see here is that the sequential version is way faster than the parallel versions. And that, of course, is because there's some overhead associated with doing parallelism. So this is a good example where the n times q model has n being very low. And q isn't really very high either. We're just multiplying values together. So because n is so small, we have more overhead to set up the parallelism than we reap the rewards from using parallelism. So that's kind of an interesting result. So that's a good example of where the n times q model will teach you some things that are important to realize when you're doing this kind of stuff. Let's see if there's anything else that's worth mentioning in this case that we haven't already talked about. I think that's about it. By the way, if you're using, if you're trying to do factorial, once you get past about 23 factorial or so, it gets to be so large it overwhelms the number of bits in a long. So that's why we're using big integers. Okay, so let's go ahead and take some questions. So for the calculation of q, we consider terminal operations. No, because that's going to be largely the same, although we did see earlier how the choice of collector can make a difference. Is it a concurrent collector? Is it a non-concurrent collector? I wouldn't get too obsessed with, precise computations of n times q. This is not something that's meant to fly people to space, in a lunar mission. It's a heuristic to give you a rough back of the envelope assessment of whether it's worth using parallel streams or not. And to be honest with you, because it's so ridiculously trivial to switch between sequential and parallel streams, in practice, you're probably better off just writing the code like I've been showing, where I can programmatically swap back and forth between sequential and parallel, and just run your code on some sample input and see what the behavior is. That's probably what I would recommend doing in practice. I wouldn't sit there with some kind of a calculator and some large equation and try to balance this out. Just try it out and see what happens. Let's see. Would using managed blocker when synchronization involved be helpful? No, it would not be helpful at all. In fact, it would make no difference and would probably, in fact, slow things down. Managed blocker, or the managed blocker API, which is part of the common fork join pool from Java 8 and beyond, only makes sense for IO-bound operations. And the intent is to be able to add more threads when some threads in the pool block on IO or block on locks. As you can see in this code, these are computation-intensive tasks, not IO-intensive tasks, or not locking-intensive tasks. And using that synchronized stuff, you're not blocking. The synchronized keyword that we have there is not a blocking call in any deep way. So it's not really worth doing. It would probably make it even slower, although you're welcome to try it out to see. Let's see. In Java 13, all synchronizers based on abstract queued synchronizer will support managed blocker. Oh, that's interesting. I wasn't aware of that. I'll have to go take a look at that. It makes some sense that they would kind of integrate that managed blocker mechanism. It seems like something that probably could also be useful for things beyond the common fork join pool. They could be used for other fork join pools as well. If the synchronization is involved, do you suggest to use parallel streams? I'm not really sure what you mean by that. So the purpose of using parallel streams as much as possible is to avoid the need for synchronization by partitioning the data up into smaller chunks and then having them run in parallel and be joined back together, all of which requires very little or no user level synchronization. There might be some stuff under the hood by the fork join pool, for example, that uses synchronizers, but even that's heavily optimized. So I'm not quite sure what you mean. There are, of course, situations where you have objects that are shared that need to be protected in a parallel stream. A good example of that, of course, would be a concurrent collector, which needs to be protected by locks because it's going to be accessed by the different threads in a parallel stream in order to update the mutable result container as the stream is being collected. So in that case, that's what you have to do. But if you stick with things like non-concurrent collectors, then you don't need to have any synchronization. So as a general rule of thumb, when you're programming with completable futures, if you're programming with parallel streams, you should try to stay away from user-level synchronization. But there are times when you need it, things like caches, for example. And if you have that, then you should make sure that you use proper concurrent collectors, things like concurrent hash maps or my concurrent hash set, in order to optimize concurrent access to those shared objects. Okay, so that's what I wanted to cover today. There's still some more things we could cover under the heading of common traps and pitfalls, or how to use Java sequential and parallel streams efficiently. But I think for right now, we will call it quits, and I'll create one or more videos from today's discussions, and I will hopefully see you all tomorrow.